Molecular Geometry, Lecture 3. When you're looking at molecular structures, you often run into multiple bonds. Let's give you a rule of thumb. A single bond is a sigma bond as a rule. A double bond is a sigma bond plus a pi bond. A triple bond is a sigma bond plus 2 pi bonds. I can't guarantee there won't be exceptions, but you're going to find this rule really holds you well. A double bond, for example, may look like this. You may have the sigma bond in here and the pi bond in here. And you see the two nuclei, the little black pieces in there that are the nuclei. Now, a triple bond may look like this. Here's a pair of models. Here's a model that we used. Look at this right here. That is a sigma bond. It is cylindrically symmetrical about an axis connecting the two nuclei. Now folks, I didn't show it very large there because I didn't want to keep you from being able to see the rest of this well. This overlap above and below is a pi bond, and it takes both of those to make a pi bond. But look in back of and in front of those nuclei, and what do you see? You see an overlap here and here, and that makes another pi bond. And that's the way you have a triple bond. It's overlapped to form a sigma and 2 pi's, and it looks almost as if the nuclei are lying in a cylinder of electrons. Let's look now at molecular orbital theory. This theory is based on the idea that when bonds form, energy is released. When energy is released, then, the molecule is going to be at a lower energy state than the atoms that originally formed the molecule were. And the diagram explaining this is called a molecular orbital occupancy diagram. Energy is released when bonds are formed. Let's look at a molecular orbital occupancy diagram for the diatomic molecule of hydrogen. Let's just call it an MO diagram for short. Now look at the two lines that you have on that energy continuum. Those are the positions of the hydrogen atoms, energy-wise. Each one has an electron configuration of 1s1. So each has one electron at this point of energy. Those two atoms collide, overlap occurs, and a bond is produced. So they collide, overlap, and a bond is produced. And when that bond is produced, it contains the two electrons. Notice the two electrons are now at a lower energy level. I've indicated their spin configuration. One is spinning one way, one is spinning the other, but they're at a lower energy. In order to move from the atomic level to the molecular level, they've had to lose energy. They are forming a sigma bond, and each one has lost Y amount of energy. I could have said X. Y just keeps it from looking funny. Each has lost Y amount of energy. So together, when that molecular structure is formed, we have lost 2Y energy. Now let's look at a molecular orbital occupancy diagram for helium. Each helium has a 1s2 electron configuration. So both of the heliums are at this point on the energy scale. Now I hear you saying, helium can't form a diatomic molecule. Do you have a theory to support that? Let's look at this. The two atoms collide, and when they do, they form a sigma bond. The sigma bond has two electrons. That is a sigma bond. It is of lower energy. But that's only taken care of 2 electrons, and there are a total of 4 electrons to be dealt with. The other two electrons must go in the remainder of the atomic orbital that is not involved in the bond. That is called a sigma antibond. A sigma antibond. And the sigma antibond from the 1s can hold two electrons. We lose Y amount of energy when the bond is formed, but we require Y amount of energy to form the antibonds. So we have minus 2Y plus 2Y tells us that there is a zero energy change when helium collides, overlaps, forms a bond and an antibond. Since there is no net change in energy, technically no bond is formed. The two atoms collide, overlap, and float away. There has been no positive energy consideration there. But where and what are these antibonds? We haven't talked about those before. Let's have a look. Consider the MO diagram for helium here. Here we have two helium atoms that have collided. Two electrons form the sigma bond. Yeah, that looks very familiar. That looks good. Okay. The two electrons form the sigma bond right here in the middle, but that's two electrons. Where are the other two? The other two electrons go into what remains of the atomic orbital. And let me do it like this. There. What's left there that I'm showing is the sigma antibond. The sigma antibond area. That's where the other two electrons are. And unlike the sigma bond, the sigma antibonds work to the destruction of the molecule. In other words, the respective nuclei are attracted to those electrons that are in the antibonding volumes also, and that prevents a net loss of energy. Antibonds are destructive unless they are countered by bonding orbitals. And if they are exactly countered by bonding orbitals, then no energy consideration has been given that will allow molecules to form. Let's consider the case for the helium-hydrogen structure, the helium-hydrogen molecule. Is it feasible? Suppose we have a container of helium gas, and into this we release a few hydrogen atoms, if we can do that. Let's say we can. When the hydrogen atoms collide with the helium atoms, will they form a molecule? Well, let's look at the energy considerations. On the left we have helium, 1s2. On the right we have hydrogen, 1s1. Suppose they collide and overlap, and when they do, a pair of electrons, and it doesn't matter which two of those three electrons does it, but a pair of the electrons goes into a sigma bonding volume. When that happens, you've lost two electrons into that sigma bonding volume, so you're going to lose 2y energy. The other electron goes where? It goes into an antibonding volume, a sigma antibond, and in so doing, it's going to gain y energy. So you have lost 2y energy, you have gained y energy, gives you a net loss of y energy. So is the structure feasible, energy-wise? Well, yes, but is that the likely thing to happen? Well, yeah, it could happen, I suppose. But is it going to stay that way? You lost a net energy of y. Suppose the helium hydride molecule were to collide with another helium hydride molecule. Do you think then that they may form a hydrogen molecule and two helium atoms? Something to think about. Bond order. Bond order is a way of describing the comparative strength of bonds. For our purposes, the higher the bond order, the stronger the bond. and any molecule with a positive bond order is feasible. Here's how to determine bond order. Bond order is equivalent to the number of bonding electrons minus the number of antibonding electrons divided by 2. In other words, what we're looking at is the number of pairs of electrons net that we happen to have in bonding orbitals. Let's calculate the bond order for hydrogen. Well, let's see, for hydrogen. Go back and look at your energy diagram, your MO diagram that you did for hydrogen. The bond order is equal to 2 minus 0. That's 2 bonding electrons minus 0 antibonding electrons divided by 2. That's going to give us 1. That is a single bond. So yes, bond order of 1 is feasible, and that is what hydrogen has. By the same token, let's calculate the bond order for diatomic helium. Go back and look at your molecule. Well, the bond order is 2 bonds in the where? In the sigma bond minus 2 in the sigma antibond divided by 2 is 0, so no bond. So the helium molecule really is not feasible on energy considerations. Well, what's the bond order for that helium-hydrogen molecule we were talking about? Well, the bond order is going to be the 2 that are in bonding orbitals minus the 1 in antibonding orbitals divided by 2 will be a half. So that's a very weak bond. So while it is feasible, it's not very strong. Keep this in mind. We're going to use it. Let's consider a molecular orbital occupancy diagram for diatomic lithium. We're talking about lithium in the vapor state. Is lithium diatomic? Well, you don't know it as one of the 7 diatomic elements, do you? But let's have a look. Here we have lithium's electron configuration of 1s2, 2s1. And I'm showing the 1s2 electrons for both of the atoms involved in the molecule. So we have a pair of electrons here and a pair of electrons here. Overlap occurs. We get a sigma bond from the 1s, which utilizes 2 of those electrons. We get a sigma antibond from the 1s, which takes up the other 2. So now we've lost both of those electrons. Now let's go to the 2s. We have 1 electron at each of these positions. 1 electron here and 1 here. They overlap and form a sigma bond from the 2s. So that looks good, doesn't it? Yeah. The bond order? Well, the bond order is 4 minus 2 divided by 2 is 1. So is lithium diatomic in the vapor state? And the answer is yes. Well then, if that's the case, why do we not memorize that as one of the 7 diatomic elements? Because lithium is not a vapor at standard state conditions, which are the conditions at which we judge the 7 diatomic elements. So lithium is only a vapor when you have heated it and driven it off as a vapor. You've caused it to boil off. Then is when it may be diatomic. Do you suppose beryllium could be a diatomic molecule? Well, here's its electron configuration. Let's have a look at it. From the 1s2, we have 2 electrons for each of the beryllium atoms. They collide, overlap occurs. We form a sigma bond and a sigma antibond. We know that we gain nothing there. Now let's go to the 2s electrons. There are 2 electrons from each of the 2s. They collide, overlap, form a bond, and form an antibond. What do you think? Well, the bond order is 4 minus 4 over 2 is still 0. So is beryllium going to be diatomic in the vapor state? And the answer is, not according to this theory, it's not. Let's go on. Let's consider the case now for diatomic boron by looking at an MO diagram. Now I don't have a lot of room on the screen, so the 1s, I've done that. You know how to do the 1s. Just don't forget to count it. Here's the 2s energy positions. We have 2 electrons here and 2 electrons here. The collision and overlap puts 2 in the bonding orbital and 2 in the antibonding orbital. Now let's go to the p's. The px, there's px with 1 in each. We have 1 here and 1 here. But where do they go? I think we need to take a further look at p orbitals and what happens when they collide. How can 3 p orbitals overlap? Well, they can overlap like this, but wait a minute. When that happens, what kind of bonds are we going to have? Let's have a look at some models. Here we have the models showing the px, the py, and the pz orbitals. Now, when these two models, or when these two atoms collide, an end-to-end overlap occurs. It looks something like this. Now, of course, when the overlap occurs forming that sigma bond, you know that that bond is much smaller than those atomic orbitals, and so the overlap is much smaller than what I'm showing here, and these outside orbitals, for all practical purposes, just about completely go away. Now, what happens when we have side-to-side overlap here? That forms one of the pi bonds. But look, do you see we also have side-to-side overlap with this orbital that is behind and in front of the screen? That forms the other pi bond. That forms the other pi overlap. And so the question then becomes, now that we see how the triple bond can form, what is the order of their energies? So we're ready to continue the electron configuration now by looking at where the pi bonds are going to come in. If you look at this, do you see that we have 2 positions there that are equivalent? Well, you need to remember Hund's rule of maximum multiplicity. You have 2 electrons to put in here. So we put 1 in this pi bond and 1 in this pi bond. That's right. Those are both pi bonds, and they're perpendicular to each other, just as we showed you in the previous screen. What's the bond order? Calculate it. Remember to count the 1s, count the 2s, and now count the 2p. Total electrons, yep. Subtract the antibonding from the bonding, divide by 2, and the bond order is 1. It acts like a single bond. And you're saying, but that's a single bond that's a pi bond. Yes, it is. It's better than the sigma bond, which would have been weaker, remember? I want you to try an MO diagram for carbon. Now, stop the video and give it a try. And then when you're ready, come back and click on the video again, and I will show you what it looks like. This is what I have. Remember, the 1s fell off the screen. Do you agree? Do you see that those 2 additional electrons coming in from the p went ahead and filled up those degenerate pi bonds? That's right. Do you agree? I hope so. Let's consider an MO diagram for nitrogen. Notice we have 3 electrons in the p. So we have 1 in the px, 1 in the py, and 1 in the pz. We have degenerate pi orbitals here, pi bonds. So I think you're going to find this very interesting. Let's see how it looks. Remember to do the 1s and the 2s now. I'm not going to let you get by without doing that. Let's fill through the degenerate pi bonds. We put 2 there and 2 there. That takes care of filling up both of the pi bonds. You've used up 4 electrons. You have 2 more to go. Where do they go? The remaining two go into sigma bonds. But do you remember where the sigma bond is energy-wise? Yeah, the sigma is of higher energy than the pi, but it's lower than the atom's energy. It goes right here. Now, it's not going to be as lower energy as the pi bond, but it's going to be lower than the energy in the atoms themselves. Remember, I showed you that. The sigma bond is overlap where there already is overlap. So there is constraint there. Well, what's the bond order for this? Don't forget, you really should think about the 1s and the 2s, even though I know they cancel each other. And you can figure it out from this. But actually, technically, it's the total electrons in bonding orbitals minus the total electrons in antibonding orbitals divided by 2 to get the bond order. But in this case, you know the bond order is 3. Now let's look at a MO diagram for oxygen, diatomic oxygen. And here's the electron configuration. Now, I want you to watch this. Don't write it down. Just watch. Now, you can do the 1s and the 2s, just like they always have been done. But I will go through and do the 2p for you. The 1s and the 2s, for all practical purposes, just fell off the screen. Okay, here we go. We have 4 electrons in the 2p of oxygen, 2 in the px, 1 in the py, and 1 in the pz. We have a total of 4. Don't you write this down yet. We put a pair here. These are in the pi bonds. Then we come up to the sigma, and we put a pair in there. Now we've taken care of 6 of the 8 electrons that are coming in from the 2 oxygen atoms. Where do the others go? Well, you're going to say, well, they're going to go into pi antibonds. And I'm going to put 1 in each of the pi antibonds, and you're going to be absolutely right. But why? Did you see them switch? You see, we were here, and the sigma bonds were higher than the pi bonds, higher in the energy status. But when the pi antibonds were formed, they constricted the pi bonds and made it more difficult for electrons to be in the pi bonds, and so this order switched. So the instant you put even 1 electron in a pi antibonding orbital, you're going to switch the orders of the pi bonds and the sigma bonds, coming from overlap of the atomic p's. What's the bond order for this? The bond order is 2. Is this molecule paramagnetic or diamagnetic? Now think about the definition, and you will remember that since this has unpaired electrons, it has to be paramagnetic. I'm going to show you a shorthand method. Look at this. This is just a generic thing here now. Suppose we happen to have 1s2, 2 atoms, they have an overlap. The 1s2 overlaps, forms a bond and an antibond. And we have a shorthand method of denoting it. We formed a sigma bond with 2. See, the sigma with 1s with 2. Then the sigma antibond, 1s with 2. And then we have, from the 2s, we have the sigma bond with 2 and the sigma antibond with 2. Let's take this a little further. When we have, say, 4 electrons, let's just do oxygen. 4 electrons in each. We have the 4 electrons, they form the sigma bond. This is the sigma bond from the 2p, and it has 2. We have a pi bond and another pi bond. Now, how do you represent them? We're putting these in order as we go along here, but their energies are different. But these two energies are the same. The two pi bonds are degenerate. So what we do is we say we have a pi from the 2p with 2, which is equivalent to the other pi with 2p from the 2p with 2. And then up here we have unpaired, unshared electrons, and these are in pi antibonding orbitals. So we have degenerate pi antibonding orbitals from the 2p, each with 1. Now this is a shorthand method that you can use to go up the energy scale by writing these out lengthwise. And that will give you a quicker way of denoting these energy levels that we've been doing that take a bit more space. Let's consider what happens when we add another electron to an oxygen molecule. Here we have another electron, and now this one has 2p5, and here's the electron. Now, when you look at it like this, we'll pair up one of the electrons that are in a pi antibond. The other one is unpaired. What's the bond order that we have here? And the bond order is 1.5. Is this paramagnetic or diamagnetic? Well, we know it's going to respond to a magnetic field because it has a negative charge. But it is also paramagnetic, so it would respond to a magnetic field even if it did not have a negative charge. How about an MO diagram for fluorine? Why don't you stop this recording right here and you work through the diagram for fluorine. Then when you're ready to see it done, just come back on and let's see if we are in agreement. So pause this now. Here's fluorine's electron configuration. I'm sure you can do the 1s and the 2s, so we will go directly to the 2p. Each one of the fluorine atoms has 5 electrons in the 2p, and I'm showing them distributed here. Now, let's distribute those 10 electrons, and I've already given you a big hint of how everything goes here. We put 2 in the sigma bond, 2 in each of the degenerate pi bonds. We put 1 in an antibond pi here, a pi antibond here, another here, and another here. And this is our distribution. Is this what you have? What's your bond order? Well, you can look at it. You hardly even have to figure it. You can look at it and tell that the bond order is 1. In other words, it is the same as a single bond. I agree, it's got a lot more than one bond in here, but all of the bonds are countered with antibonds except for the equivalent of 1 bond. Is it paramagnetic or is it diamagnetic? And the answer is, it's diamagnetic. All right, let's move on. Let's look at neon. 2 neon atoms collide, overlap. Will they bond? Well, we've got 6 from each of the neons, 12 electrons to distribute. I'm sure you can run this through really rapidly. You can do the 1s and the 2s. You know how to do that. We'll just look at the p's right here. Here we go with a sigma bond, 2 degenerate pi bonds, 2 degenerate pi antibonds, and a sigma antibond. Just that easy. Is the neon molecule likely to form? Well, the bond order is 0, so no, the molecule is not likely to form. There's been no positive reason to do that. No net loss of energy. Now, the third period is going to follow the same pattern that the second period does. It's just more of it. You're going to have to use a longer sheet of paper. Or, if you will, you can do it in the shorthand method, but it follows the same pattern. Well, let's look at a heterogeneous molecule now. And the heterogeneous molecule that we're going to talk about is carbon monoxide. Now on the left, I'm going to give you the electron configuration for carbon. And on the right, I'll give you the electron configuration for oxygen. And we'll start at the very beginning and go all the way through. So here I have the 1s2 from carbon and from oxygen respectively. 4 electrons. They're going to overlap, and what's going to happen? They're going to form a sigma bond. Then they will form a sigma antibond. So nothing has been gained from the overlap of the 1s orbitals. Let's go to the 2s now, each of which has 2. We have 2 electrons in each of these orbitals. They're going to overlap, form a sigma bond, and a sigma antibond. Once again, nothing has been achieved by this. So now let's go and look. Here we have the p orbitals. Carbon has 2 in the p, oxygen has 4. We have a total of 6 electrons, and we don't have to match up a carbon electron with an oxygen electron. It's fine. You've got 6 electrons total. They don't know whose is whose. So we're going to distribute the 6 electrons. We'll put 2 in each of the degenerate pi bonds and 2 in the sigma bond. Now remember, there are no pi antibonds here. There are no pi antibonds because by the time we finish the sigma bond, we have used all of the electrons. That is why the degenerate pi bonding orbitals are of lower energy than the sigma bonding orbital. Remember? Good. What's the bond order? The bond order is 3. Well, I think you're ready for a summary and review, aren't you? We've discussed 3 bonding theories. We've discussed VSEPR. We've talked about the valence bond theory. And we've talked about the molecular orbital theory. And the questions ask, which is the best theory? Well, they deal with different things, remember? VSEPR deals with geometry. Valence bond theory deals with sigma and pi bonds. And the molecular orbital theory talks about bonds and antibonds. VSEPR deals very specifically with geometry. Valence bond theory talks about specific parts of the molecule, the sigma bond part, the pi bonds, and things of that type. Molecular orbital theory talks about the molecule overall as it addresses bonds and antibonds and allows us to go through and figure bond order and strength of bonds and so forth. So which is best? It depends on the information you want. But probably your MO theory is the broadest, the most all-encompassing. Is that enough about bonding? A better way to teach and learn chemistry.